Greetings to everyone. First, let me introduce myself and my partners. My name is Elita, and my partners' names are Meda and Gavin. Now, we want to present to you about our selected paper. The title is Neural Network for Earthquake Prediction based on Automatic Clustering in Indonesia. Please enjoy. Part 1 Introduction. Indonesia has a high risk to geological disasters as it lies between three active plates of the world, the Eurasian, Indo-Australian, and Pacific plates. Therefore, a system that's able to predict the earthquake will greatly help to minimize the risk of losses that arise. A series of earthquakes follow a special pattern with a trigger that results in earthquake event. In other words, natural disaster. However, an earthquake prediction shows that where, when, how big, and how probable the predicted event is. Several studies applied artificial neural networks, or ANN, for earthquake prediction. Seismic clustering is the first step to analyze earthquake risk which based on a variety of seismology criteria. The data used are seismic data of all regions of Indonesia obtained from BMKG and USGS. This study proposed an ANN model to predict an earthquake during the next 5 days after an earthquake occurrence with magnitude equal or larger than given threshold for a selected cluster in all regions of Indonesia.
Research method. This section describes the system design of earthquake prediction. Figure 1 illustrates the overall process. A. Data acquisition. The earthquake data covers the entire territory of Indonesia, which is the boundary 5.98 north latitude, dash 11 south latitude, and east longitude 94.12, dash 140.98 east longitude. The earthquake dataset in this research is taken from Catalog of Agency Meteorology, Climatology, and Geophysics, or BMKG, and United States Geological Survey, or USGS, from 1910 to 2017. The magnitude of completeness of the catalog for earthquake dataset is determined first before implements clustering process. It uses the Gutenberg-Richter frequency size distribution.
B. Cluster analysis. The main objective of cluster analysis is to generate groups of data from a large dataset into small groups with the same characteristic. Group clustering result will produce an accurate representation of the behavior of a system. This concept is to extract the most similar separated sets of objects according to a given similarity measure. Thus, this algorithm is the basis for extracting the dataset to obtain useful information for finding pattern recognition in the data. The first process is to find the number of clusters. The number of clusters are the amount of clusters to group large data into small groups. There are many algorithms to determine the number of clusters. The easiest method to find the number of clusters is to generate randomly, but this method does not guarantee to find the global optimal. Choosing a large number of clusters does not necessarily imply better for clustering. On the contrary, results call less accurate representation. Therefore, the optimal number of clusters has to be determined. Since the number of clusters selected to cluster dataset is one of the most critical decisions in clustering techniques. Several approaches have been developed in order to determine this number. The second process is to cluster the dataset into a particular cluster based on the most similar. Before running this process, it requires an initial cluster. Therefore, the number of clusters obtained from the first process becomes the initial cluster for clustering dataset. In this paper, data clustering uses hierarchical k-means clustering. It combines two clustering algorithm, hierarchical algorithm and k-means algorithms.
Next, part 2, research method. C. Proposed neural network. This is the image of architecture, the neural network model for predicting the earthquake occurrence. The input neuron layer has 7 nodes representing the 7 seismicity indicators. They are used to recognize the pattern of earthquake occurrence. It can also be employed for predicting the nature of the future events, and as well as mitigation of earthquake risk. To find seismic parameters, firstly, the earthquake data should be clustered into small data groups based on the optimal number of clusters. Then, distribution of data is utilized to investigate the seismic parameters for each clusters. 5 input parameters or B-value were obtained from the Gutenberg-Richards laws. The 7th input variable identifies the probability of recording an earthquake with magnitude large. This input is to include Gutenberg-Richards law in a dynamic way, which is calculated from the probability density function. The output parameter has one variable y. Y parameter is the maximum magnitude observed in the cell under analysis during the next 5 days. It has been set to 0 for such situation where no earthquake with magnitude equal or greater to m, where the time t is measured in days. The input vector or x has 7 elements, and the output vector or y has a single element. The number of hidden layers and the number of nodes in each hidden layer are determined by trial and error for best results. First, one hidden layer and several nodes are arranged. The number of nodes is increased gradually to see the pattern of the movement of the result. When the number of nodes is increased but no improvement in its value, the experiment is stopped and the best result is taken.
Part 3, Result and Discussion. In this section, it is explained the result of research and at the same time is given the comprehensive discussion. A. Dataset clustering. Grouping dataset into small groups is well known as clustering. There are 3 steps in this stage. First step is to get optimal number of clusters, while the second step is data clustering process, and the last step is visualizing on map. To visualize the results of clustering process, it uses PHP or Java Bridge tool and Google Map on Indonesia Map. Every cluster has different colors in order to differ one cluster to another. Visualization of spatial data distribution based on clustering.
Part 3, Result and Discussion. B. Seismic parameters extraction. The earthquake catalog used in this paper has been obtained from the BMKG and USGS service. Before analyzing earthquake parameters, the completeness of the data each area should be analyzed first. Year or completeness of seismic catalog can be graphically calculated. On the graph, the time is inversely plotted to the x-axis and the accumulated number of quakes on the y-axis. The slope of the curve, which represents the annual rate in the data, has a straight line on the curve showing that at that time span is constant. From this image, the earthquake data is obtained in the estimated time frame from January 1975 to May 2008 for data training.
C. Neural network training and testing. Network training uses earthquake catalog between January 1975 to May 2008. It consists of 1 training dataset for cluster 0, 369 training dataset for cluster 1, and 759, 739, 1009, 1113 training datasets for cluster 2, cluster 3, cluster 4, cluster 5. Sample of training datasets for cluster 0 are present in table 4. The model was tested using earthquake catalog between June 2008 and December 2016. It also consists of 489 datasets for cluster 0, 152 datasets for cluster 1, and datasets for cluster 2, cluster 3, cluster 4, cluster 5 are 237, 199, 307, 318. Sample of testing dataset for cluster 0 showing 7 elements and 1 output parameter are present in table 5. The best result according to trial and error is the ANN model with learning rate set to 0.1 to hidden layers with 32 nodes each other and then 1000 iteration. Next, part 4, conclusion. An ANN model has been built to predict an earthquake during the next 5 days after an earthquake occurrence in a selected cluster. The best result according to trial and error is the ANN model with learning rate set to 0.1 to hidden layers with 32 nodes each other and then 1000 iteration. The proposed model gave better performance for magnitude thresholds more than 6.
Okay, that's all video presentation of our group. Thank you for your attention.